So, in the previous lecture we derived a relation between acceleration dv dt and force F on a particle, and we found that it is a bit complicated relation. F equal to ma does not simply translate into something similar in relativity. Of course, that complicated expression also reduces to F equal to ma in low velocity limits. Then we took an example where a particle which was at rest initially was subjected to a constant force, and we saw how the velocity increases with time, and we saw that no matter how much time you apply the force, the velocity is not going to reach c, or those things we did. The simplification was that velocity was and force, they were all parallel all the time, and therefore, the equation was little bit simple. Today I will start with a question where this will not be the case. The velocity and the force will not always be parallel or always be perpendicular to each other. So, it will be a two dimensional curved motion. So, the problem is the following: a particle having charge q and mass m naught is projected with speed u in y direction in a uniform electric field E that exists in x direction. You have to find the velocity as a function of time. This is the question. So, you have a particle q, charge q, which is projected in y direction. So, the initial velocity is this initial velocity, and then this whole region you have an electric field E. So, force on the particle is q times E. I have written this E, and there is a reason behind this. So, force is q times electric field, and since this is uniform and constant as a function of time, it does not change. So, wherever the particle goes, it finds that electric field. So, this is the force, and we have to find the velocity as a function of time. The force will be in x direction all the time, and so you will expect that the motion will be a curved motion. So, how do I get velocity? We can write this f as dp dt, this is qe, and therefore, dpx dt is q times e, because the field is in x direction. So, this is the magnitude of the field, and dpx dt, whereas dpy dt is 0. In y direction there is no force, and therefore, this is 0. So, from here you can write px is equal to qet, right, because this is constant. So, you can integrate dpx is qe dt, and then you integrate, and then you get px is equal to qet. Initially there is no linear momentum component in x direction. So, there is no integration constant here, and this equation will give you py is equal to constant, that is p naught, that is initial linear momentum here, m naught times u divided by square root 1 minus v u square by c square. So, that will be this, but this will be constant. So, this is it. From here we can try to find velocity components vx and vy, but it is not going to be easy, because when you write this px will be m naught, this px I am writing m naught vx divided by square root of 1 minus v square by c square. Remember, this v is the speed of the particle, whereas this vx is only the x component. So, that gets involved here. So, this is vx square plus vy square, and that is qet. So, from here getting vx as a function of time is not trivial, because vy is involved here, and similarly py is p naught, but py is m naught vy divided by square root 1 minus v square by c square, that is py, and that is equal to p naught constant. that is constant. But even then getting Vy is difficult, because you also have Vx square here. This is Vx square plus Vy square, and Vx will be obtained from here, and that is also not very simple. So, this is also not very simple. So, getting Vx and Vy velocity from these equations is tricky. Now, I am going to give you a very useful technique in solving such kind of problems, and that is, use this relation. If you want to write velocity, this is p divided by that m naught gamma relativistic mass v, that is the definition, p is equal to m naught v gamma. So, this is m naught gamma, and for gamma you can write m naught E by c square. This m naught is also not necessary. Okay. So, E by c square. What is E by c square? This is the total energy. Remember, this is the total energy. What is E? The total energy. Total energy is m naught c square gamma. So, instead of this m naught gamma, you can write just E by c square. So, V is p c square by E, and total energy, if you have a particle, the total energy, the kinetic energy and plus the rest mass energy, that is here. So, you can use this relation. So, if I have Px is equal to Qet and it take x component here, I get Vx is equal to Px c square by E. Remember, this E is not constant, this E is changing with time because the particle is gaining kinetic energy. So, this is not constant, but then you know what it is, this will be Q and then this E T c square divided by square root of m naught square c4 and plus p square c square, and that is Qet c square divided by square root of m naught square c4 and plus what is p square? It is px square plus py square. So, this Qet square and plus p naught square, that will be p square. So, it is Qet square and plus p naught square and then c square, this c square, this p square I am writing here, p square is px square plus py square, that is this. So, we have gotten Vx as a function of time, right, because p naught is constant, we know it, this is the initial momentum here, initial momentum m times u divided by square root 1 minus v square by c square. So, we know that, and this is time, these are all known quantities. So, you get Vx. So, this is a very powerful simple relation which can be used to get velocities in a very simple fashion. Similarly, Vy, can write Vy will be equal to Py, and Py is P naught. So, it is P naught c square, by same total energy. So, the same denominator, m naught square c4 plus Qet square plus p naught square and c square. So, that is it. Now, let me go to one more problem. So, here is the problem. A particle with charge q and mass m naught is projected in a uniform magnetic field B. The initial velocity u is perpendicular to the field B. Describe the motion. So, this is a very standard problem if a particle, charged particle is projected in a magnetic field perpendicular to it, it goes in a circle with frequency, angular frequency qb by m. So, that same problem here, but now relativistic equations to be used. Now, our equation was dv dt equal to f divided by m naught gamma and then minus f dot v and then v here, and then we had m naught c square gamma. Now, in this case it is a magnetic field charged particle. So, the velocity and force, they are perpendicular all the time. F is q v cross b. So, force is perpendicular to the velocity and force is also perpendicular to the magnetic field. Since force is perpendicular to velocity, this term will not be there, this term will be 0, and you will have a simple relation dv dt is f divided by m naught gamma. So, that is one great simplification. And then it is also perpendicular to the field B. So, if B is in say z direction, suppose B is in z direction, then this force has to be in xy plane, because it is a cross product with B, and initial velocity is perpendicular to B. So, initial velocity u is in the xy plane. So, if the initial velocity u is in xy plane and the force is always in xy plane, there is no way it can pick up the z component, and hence the first thing is entire motion will be in xy plane. So, that is one. And then we can analyze, we can write what is dp dt. dp dt is this force, and that is q times v cross b. So, let me write it Vx I cap plus Vy j cap and cross b k cap, which will be q Vx b with a minus sign, I cross k will be j, minus sign is here, and then plus q Vy b I cap. So, if I take x and y components, I will get Px is equal to dpx dt. So, dpx dt is equal to q Vy and then b, and dpy dt will be j component, y component, that is this minus q Vx b. I can write this in terms of Vx and Vy, and for that again I will be using that same equation, V is equal to P and C square here and E here, this is the total energy. Okay. Because from here if I try to write dVx dt, it will be difficult because of that square root 1 minus V square by C square coming in all the time. So, if I use this, and from here I can write dVx dt is equal to dPx dt and then C square by E, and dPx dt I know, dPx dt I know, it is q times Vy times b, and that into C square by E. So, that is dVx dt. And similarly, you can write dVy dt, dVy dt will be dPy dt and then C square by E, which is dPy dt is minus q Vx b and then c square by E. So, now I have nice relations. I can write q into b into c square by E, this write as omega, q into b into c square E, same thing here, q b into c square by E, I write this omega, then I have dVx dt is equal to dVx dt is equal to omega times Vy, omega times Vy, and then dVy dt is minus omega times, I put a double minus here, dPy dt is this, just one minus. So, it is minus omega times Vx. Now, these are exactly the same equations which you get in non-relativistic case. Only difference is this omega is not this much, omega is qb by m. So, is the same equation, if you are in non-relativistic region, non-relativistic speeds, then you get the same equation with omega as qb by mass, it is this. So, in terms of omega, everything is identical, and therefore, this will be again a circular path, and the angular frequency will be given by this quantity qb c square by capital E. This is the total energy, remember, and now you can write that if you write this omega naught, this omega, this actual omega, this omega is q b c square by total energy, but E by c square, you know what it is, E by c square is just m naught times gamma. So, it is q b by m naught and then square root of 1 minus v square by c square. So, with that much of change, it will be the usual circular path in a uniform magnetic field. Okay, now another topic, just I will just give the equations and not practice much on that, and that is transformation of force if you change frame. What I have done today and in the previous lecture was, I was in one frame, my particle was moving. So, there was force, velocity, acceleration, and we try to describe that motion from this one single frame. Now, the question which I am going to address is, if I see that there is a force in this frame, and then if that same force is seen, there is a force on a particle, particle's motion depends on frame, from which frame you are seeing. So, if I change frames, I know how to change velocities, how to change positions. We can also work out how to change accelerations, but how to change frame, how to change force in the frame, that also is a question, and we will just see that the force also depends on which frame you are seeing it. So, I will again depend on F is equal to dP dt. So, I am still thinking of a particle, I have a particle in mind, its rest mass will be some m naught, and at time t it will have some speed, some velocity, which you can have a u symbol for that. Now, this dP and this energy, you remember energy and momentum, they make a 4 vector. The 4 vector was energy momentum 4 vector in E by C, and then Px, and then Py, and then Pz, that makes a 4 vector. So, at a particular time the particle has some total energy E, some total linear momentum which has components px, py, pz, then at time t plus dt these things will change a little bit. So, you have E plus dE, px plus dpx, py plus dpy, pz plus dpz, but that also will form a 4 vector. And when you subtract, difference of two 4 vectors is also a 4 vector, addition of 2 vectors is also a vector in the same spirit, and therefore, if I write dE by C, dpx, dpy and dpz, this also forms a 4 vector. And since this forms a 4 vector, it will transform as you go from S to S prime, it will transform according to the Lorentz transformation equations. So, in the primed frame, if this is the value, and then you will have that transformation matrix, the same Lorentz transformation matrix, and here it will be dE by C and then dpx, dpy and dpz. And your S and S prime, if that is a standard definition that we are using from the very beginning, S prime moves in x direction with a velocity v, positive x direction at the time of origin crossing t equal to 0, t prime is equal to 0, all those things. If I am sticking to that, then this Lorentz transformation, you know what it is, that gamma beta, that transformation, and then you will have, remember, let me write, if you have Ct here, x here, you have y here and z here. So, that will be same transformation matrix, and then you will have Ct here and then x, y and z here. And then this transform, look at this transformation, this one, for this it will have these two terms, and x prime is equal to x minus Vt divided by square root 1 minus V square by C square, and this t is this Ct divided by C. Okay. So, that is it, and in the same way this dpx will be related to these two, and you will have dpx prime is equal to, dpx prime will equal to dpx minus v times, and then the first one, this one divided by C. Okay. Since it is the same matrix, so whatever is the form here, that will be the form here. Here it was x prime equal to, so I am taking dpx prime equal to, then it was x minus, so x minus, so I am taking dpx minus, then v is here, t, this t is Ct divided by C. So, similarly here it will be dE by C divided by C, so dE C square, dE by C square, and then the denominator will be 1 minus V square by C square. So, that is how dpx prime will transform. And how will dt prime transform? Very simple, very simple. You can take again the differences, this will be C dt prime, then it will be dx prime, dy prime, dz prime, this will be C dt, and then you have dx, dy and dz. And you know what is the transformation of this is t prime or dt prime. So, dt prime is equal to dt minus v dx by c square and then divided by square root of 1 minus v square by c square. This we had been using from the very beginning, t prime is equal to t minus vx by c square divided by square root 1 minus v square by c square. So, here only we have dt prime and dt and dx, otherwise this transformation is same. So, this is a transformation of this component, time component. Now, we have dpx prime, we have dt prime. So, divide, what do you get? What do you get? dpx prime divided by dt prime. This is nothing but fx prime. So, divide this expression by this expression, the denominator cancels out, and therefore, you have dpx minus v by c square de divided by v by c square de divided by dt minus v by c square and then dx. Remember, what is dx, dy, dz is the displacement of the particle as seen from S in time dt. So, this is it, divide by dt, this is equal to dpx dt, then minus v by c square de dt divided by 1 minus v by c square dx dt. First, let us look at the denominator. This is 1 minus v by c square. What is dx dt? Dx is the displacement in small time interval dt as seen in the S frame, and therefore, dx dt is the x component of the velocity of the particle as seen from the S frame. So, this is ux, this is ux, the particle is moving at time t, the particle is moving with this speed u in S frame, x component of this velocity that will appear here, and here dpx dt will be f minus v by c square, and de dt. What is de dt? What is de dt? What is E? E is m naught c square plus k, kinetic energy, rest mass energy plus kinetic energy is total energy. This is constant. So, this is dk dt, this is dk dt, and change in kinetic energy, you know, it is f dot dr, f dot dr. Remember, this is all S frame quantities and this is S prime frame quantity. So, in S frame I am writing this. So, f dot dr and dt here. So, this is f dot v, this is f dot v. So, it is f dot v. F dot u, dr dt is the velocity of the particle as seen from S frame. So, that is this u vector. So, this is f dot u. So, that is the transformation between fx prime and fx. This is fx. So, it is not only fx coming in, it is fx, fy, fz, everything coming in, and then this particle velocity is also coming in. So, that is how the x component will transform. And for y component transformation, fy prime will be dpy prime divided by dt prime. And what is dpy prime? What is this quantity? dpy prime, third component in this 4 vector, third component in this 4 vector, dy prime is equal to dy, y prime is equal to y. Similarly, here dpy prime will be just dpy. So, this is dpy, and then dt prime is of course dt minus v by c square, and then dx here, okay, and then divided by square root of 1 minus v square by c square. Remember, v is the frame velocity and u is the particle velocity in S frame. Make this difference. This v is the frame velocity which is coming in Lorentz transformation, and u is particle velocity in S frame. So, again divide by dt. This is d p y dt. So, I am dividing by dt here, and I am dividing by dt here 1 minus v into ux by c square. So, this is f y square root 1 minus v square by c square, and then divided by 1 minus v ux by c square. So, that is how the y component will transform, z component will transform similarly, and x component will transform according to this. So, if you are solving problems where forces are acting, motion is there as seen from one frame, and you want the corresponding equation, corresponding quantities in S prime frame, you have to transform forces also according to these equations.